things here. So we've got all these practice exams. We'll kind of go through practice exam B today. So one thing that I put up there last week, a little bit after the fact, let me see, here we go, is that practice exam A, and it kind of has more detailed answers, like how I would work through these, okay? So that's up there on Canvas. If you go to that exam 1 practice materials, kind of got that detailed answer key. It looks like I've got one for B as well, right? So you can kind of look through both of these, see exactly how these are worked out. I'll go through them today. I'm going to start, if anyone's looked at those, if you have specific questions, I can start with those problems. Your formula sheet, which will also be given to you in class on the exam on Wednesday, is up there. So I have them written. They're actually, I picked them up today. They're all printed out. It's going to be, I believe it's 16 questions and then 4 short answer. The short answer are really just questions you would see in these practice exams, just with no options. And so there I'll grade for a little bit of partial credit, but only for those last 4, right? The first 16 are just multiple choice. You get the points if you get it correct, or, if you get it incorrect, you don't get the points. And those last 4 are a little bit trickier. And so I want to see your work, and if, I'll grade it for partial credit. So even if you get it wrong, if you're really close, you'll get the majority of the points there. Okay? Yeah.
For the first 16,
you don't have to show any of your work for the first 16. Hopefully you have some work in front of you. You can work on the side or do whatever you want. But I won't grade for any partial credit for those first 16, just those last 4. And I'll reiterate that again on Wednesday.
Oh, how many points is it?
So it'll end up being, and actually I think I just lied to you because I think I added a question on there as a bonus question. So it's out of 105 points. So that's the total you could get, but it's graded out of 100. So if you get every single question correct, you actually end up with more than 100%, right? It's because I know that some of them are tough. Basically, you kind of get one that you can get wrong. It's kind of a freebie, right? So even though it's a bonus question, really every question is worth the same amount of points. And it's just that I only grade you out of basically the questions -1, right? You kind of get one freebie question there, okay? I'll print out these formula sheets for you. One thing I don't remember if I mentioned to you as on Wednesday, but I think a really good practice is, where is it? There it is. Print this formula sheet out and maybe try to write down next to every formula what it means. So here was one where we're using Bayes' theorem, right? We'll work through an example of using this one today. And as we go through it today, it'll be a little bit easier. I'll help you identify some of these. But then as you're studying, kind of looking at this formula sheet with everything written down next to it, even though the formula sheet you get in the exam will look exactly like this, maybe a good thing to do, if I've been studying with this one where I've had everything kind of written down next to what it means, then when I see this, the first thing I might do is write down next to the formulas that I tend to forget. Oh yeah, this is Bayes' theorem. Here's my discrete random variables. Here's my Poisson, right? Write that all out right away. And then, you kind of have those kind of labeled as you work through the exam. Yeah.
So we're going to be able to write on the formula sheet.
Once I hand it out, right? So I'm going to print them out for you. So you'll all get this. This is what you'll get. But as soon as I hand it out, you can write wherever you want, right? I don't care, you can write all over the formula sheet. You can write on the exam. Yeah. Yep. Any other questions related to kind of the procedure of the exam? So make sure you bring a calculator. I will bring an extra one, but if more than one of you forgets your calculator, we're going to have issues, right? It means you're going to have to share. It's going to be kind of tough. So make sure you bring a working calculator with you on the exam. I think it was asked last week, but I won't ask anything related to Excel, right? So you don't have to have like any of the Excel functions memorized. Like, I'm not going to ask questions on that. It'll look very similar to the practice exams. Those will be your best study tool here the next couple of days, okay? Any other questions from me? Okay, so I'll probably sit here a little bit more for the rest of the class, just because I think we can get through more problems from me switching back and forth to the formula sheet and then the practice exams. But I do want to start out, we'll kind of use this Poisson distribution right here. I want to show you an example that we didn't quite get to at the end of last week, but is fair game for the exam. So with this Poisson, this was the idea that we're looking for a certain number, or the probability of a certain number of successes over some given interval, right? And I said for the exam, I'm going to keep this at time intervals. Okay. So one thing over here we could see is let's say on average, I don't know, that every week, maybe something a little bit different here. So let's do 14. So we'll do the average rate over this week of the number of car accidents or something we see out on a specific road is 14. Okay? We're then interested in finding the probability of exactly 3, but instead of this week, right? If it was just 3 this week, it'd be just like the other examples we were doing on Wednesday. I'd have my average rate of change at 14. I'd have my X value of 3, plug them into that probability mass function for the Poisson, and I could get that probability relatively easy. Now, what if I wanted the probability that I see 3 car accidents on that road tomorrow in one day? Well, I have the average rate over a week. Okay, so what do you think? One thing I could do, if I want the number of successes on a day, I can convert my average over the week to an average over the day. So I see 14 a week on average. How many am I seeing each day? 2. Yeah, 2, right? How'd you do that? You just divided by 7, right? So what you did there, you're going from a larger to a smaller time interval. You're going to take that old average that you had here, that weekly average, and you're going to divide it by some factor, right? Here the factor was 7, right? Because there's 7 days in a week. If I was going from an hour to a minute, I would divide by 60, right? There's 60 minutes in an hour. If I'm going to go from a year to a month, I'm going to divide by 12, right? There's 12 months in a year, right? And I'll if I ask you, which I wrote the exam, so I probably know, but if I ask you something like this in the exam, I'll probably even be annoying about it and tell you something like, you know, a reminder, there are 7 days in a week, or a reminder, there are 12 months in a year, right? So I'll make sure you know those factors, but they should be, I'm only going to use like really common ones. It's not like I'm going to go from a mile to yards or something like that. I'm keeping it at time, and it'll be time that relative, you know, we're all kind of used to. So if I'm ever going from a larger to a smaller time interval, I'll divide by whatever that factor is. Right? In this case, divide by 7. So 7 days in a week. We went from an hour to a minute. Right? Divide by 60, right? Because there's 60 minutes in an hour. Now that I have that new average in the time interval that I want, now it's just like everything we did before, and it becomes pretty easy. So I'll take lambda to the x times e to the negative lambda, and then divide by x factorial. So once I convert my average rate lambda into my new time interval, it's just like what we were doing before. Okay? I don't know what this is off the top of my head, what, right? We have to enter this into our calculator. I can do that here in a second if you want to double check it. But right, we can deal with this 3 factorial. Hopefully by now you've all kind of found where that factorial button's at in the calculator you want to use. Even if you didn't, this one would be easy enough, right? 3 factorial would just be 3 times 2 times 1. Okay. So that's kind of how we change our time interval, right? I want to go from a larger to a smaller. Any questions on that? Like I said, it'll be year to a month, week to a day, hour to a minute, something like that. Right? Nothing crazy. If I ever want to go, let's say I want the probability. This one would be kind of wild, so I would use a slightly different example here. Probably wouldn't do something like this, but let's say I want to know what's the probability that I see 100 car crashes over the year, right? So now I'm going from a smaller to a larger time interval, right? I'm going from a week to a year, right? So I need to find the average rate over a year. Right? So how would I do that? I'm going to go, there's 14 every week. How many are there going to be in a year? When I multiply by that, how many weeks are there in a year? Yeah, right? I'd multiply by 52. Now, I wouldn't give you an example like this because this ends up being a pretty high average rate. If I plug in 100 factorial, I can't do that in my calculator. I'm just using this as an example of something where we're going from a smaller to a larger time interval, so we don't have to change all of our values to that. So what did I do here when I wanted to go from a smaller to a larger time interval? I took my old lambda for whatever time interval I had, and I multiplied that by some factor. Right? So if we're going from a larger to a smaller time interval, we divide. If we're going from a smaller to a larger time interval, then we multiply. Okay? And that's fairly intuitive, right? If 14 happen every week, then 15 or 14 times 52 happen every year. Then I would take that new lambda, plug it in to where my lambda's at, plug 100 into my x. Like I said, obviously that specific one with those values, we couldn't do this on our R calculators. We would need some type of higher powered computer to do that. But this would be the process that we use. Okay. So it might be a good thing to jot down. Any questions on that? So that's fair game. Really, the only thing new I'm introducing here, though, like we're still using that Poisson. The only kind of difficult part there is kind of converting your lambda into this new time interval that you want. Okay. Questions on that one? All right. So we'll be a little bit more stationary here, but I can always get up and use the board. So if what I'm doing up here, you need more, feel free to ask and I can do that. So that was our Poisson distribution equation. I'm going to go over the ones I think are probably the best for you to see on this practice exam. So let's start with practice, unless there's any specific questions that anyone has if you've been looking over these that you would like me to do. Or is there a specific type of problem or topic that you find difficult that you'd want to see problems on? No? Just everything, right? So I'll start out with what I think is probably one of the harder problems on the exam. I do kind of like this example. So let's say we have something like this, right? We're given all this information, right? So one thing I might do, I'm just going to give myself some space here. If I had space on the exam or an extra piece of paper, and I'll bring blank paper too you can write on. I would first identify, notice I've got what, 3 questions related to this. I'm just going to identify everything this question gives me. Right? So we've got major concerns of steroid use, and there's a manufacturer that claims that their drug test will show a positive result given that the athlete is using steroids with a probability of 0.95. Okay? So I'm going to say the probability that this test shows positive, right? Given, and I'm going to space this out, given, right, what we're given that the athlete is using steroids. So given that they're using, the probability we see a positive test result, right, is told to us to be 0.95. Okay. We're also told that the drug test shows a positive test result, given that the athlete is not using, that probability is 0.01. So given that they're not using, right, the probability that the test comes back positive is 0.01. Okay. And then finally, we're told the probability that a random player is using steroids, so the probability that someone is using steroids without any other information is 0.15, right? That's coming from this line right here. Okay. So I've just identified the 3 pieces of information that this problem gave. So the next thing I'm going to do is go down here and look at this question, right? So what's the probability that the athlete is using steroids and they test positive? Okay. So here, I guess I'll write it up here. What I'm looking for is a probability that they're using and this test comes back positive. And you can shorthand this however you want, right? I could have just wrote positive in here or negative, but here I'm just going to write out that the test is showing me that it's positive. Well, if I want the intersection of 2 events, and I go to my formula sheet, scroll up here, and it kind of reminds me that I can find the intersection of 2 events by taking that conditional probability and then multiplying by whatever I'm conditioning on. Remember, what I'm conditioning on is what's on the right-hand side of that vertical line. Okay. So we'll go back and be able to, if I can remember which one I'm on. Oh, this is the answer key. That doesn't help. There we go. So this should just be equal to the intersection of these, or sorry, the intersection of these two should be equal to the conditional probability. So I can say the probability that the test comes back positive, given the person is using, multiplied by the probability of what I'm conditioning on, which here is just that the individual is using. Right? So I go up here, what was I given? Well, in fact, I have this probability, that would be 0.95. I also have the probability someone is using, which is 0.15. And I'm done. Right? So you can find the intersection of two events by taking a conditional probability. Notice kind of my A and my B, that was kind of switched there. Multiplied by what I'm conditioning on, which was here that they're using. And then it's a matter of plugging in those probabilities identified initially. Okay. So I think that is 0.143, right? If we actually plug that into our calculator. Okay. Any questions on that one? So the next one is, what's the probability an athlete is not using and test positive for steroids? So we basically have the exact same setup, but now instead of using, it's what's the probability they're not using, and the test comes back positive. Right? And if you're writing this out, when I write and, right, I could take a little bit more time, but I'm trying to not waste too much time, and I could put in, right, that intersection symbol, right? Those mean the same thing. Well, once again, this is just equal to the probability, conditional probability, multiplied by what I'm conditioning on. It's just now I'm looking at what's the probability the test comes back positive, given that the individual is not using. So now what I've conditioned on is that they're not using. So now I'll multiply by the probability they're not using. Okay. Once again, I go back up here. I was given this conditional probability. So that was 0.01. And the probability the individual is not using, well, I don't have that. Right? However, I know if the probability that someone is using is 0.15, what should the probability that they're, there we go, not using be? There's only two states of nature. I know they have to add up to 1, so 0.85. Okay. So now that I've got that, I can plug that in and I can get my answer here, okay? Which should be, what, 0.0085? Any questions on that? So notice I wasn't directly given the probability that someone's not using, but if I know the probability someone's using, I automatically know the probability they're not using is just whatever would get me up to 1, if you want to think about it that way, okay? Any questions on those two? So we haven't had to use Bayes' theorem yet. Those two are kind of leading us into there. But 13, just going to write out what we're looking for. So given that the test comes back positive. So given that the test comes back positive, right? What's the probability the athlete is not using steroids? So given that the test comes back positive, what's the probability that they're not using? Okay. So I think the best thing to do here, right? Well, give you a non-so-technical answer. You'll notice the practice exams are written in a pretty similar order, okay? So the exam will probably look like a similar order as well. If you look at this and you say, okay, I got a conditional probability. We were trying to find, we dealt with those a little bit earlier, or we've dealt with those in past. Oh yeah, that's just the intersection of two events divided by the probability of what I'm conditioning on. If I try to write this one out this way, I'm going to run into a problem, okay? So I'm going to I'll show you that first, and we'll see why we can't do that. So not using, and the test comes back positive, and then we'll divide by the probability of what we conditioned on, which was that the test comes back positive. So if I look here, do I just have the probability a test comes back positive? No, I only have conditional probabilities that the test comes back positive, right? If you tell me that someone's using or you tell me someone's not using, then I can tell you the probability the test comes back positive. But if you just say, if I choose a person at random, what's the probability? I don't know from the information I was given, right? That's where we said, okay, using, and I had a whole slide and matched with the colors where we were substituting equations in. But ultimately, we know that the final equation that we can use to solve this is going to look something like this, right? So we have RE, which is the outcome of the test that we see, and the S, which is the state of nature we're interested in finding the probability of. Okay. So if we look at our equation, let me see if I can get this to go hand in hand. This might be a little tricky, but I think I can do it. Okay. So we just tried writing it out this way using kind of the more simple formula, but we didn't have those probabilities. So what I'm going to do now is my S, the state of nature I'm interested in, is a probability that they're not using. The outcome of the test I see is that it came back positive. So I'm just going to write this out in the context of my example, right? So my S, right, my state of nature was that they're not using. So not using, right, multiply by the probability of E, which my E is that the test comes back positive, given that someone is not using, the state of nature I'm interested in. That's my numerator here. So let me get fancy. Oh, where's my equation? There we go. Then I'm going to, there we go. Okay. Maybe I put this above here so it's a little bit easier to see. Well, now notice the very first part of my numerator is the exact same thing as my denominator. Sorry. The first part of my denominator is the exact same thing as my numerator. So really, I could just write this out again, right? I'm looking for the probability that someone's not using, multiply by the probability the test comes back positive, given they're not using. And then I'm going to add to that the probability of S complement. So if S was that they're not using, what would S complement be here? Yeah, that they are using. Multiply that by the probability of E. Well, my E was that the test came back positive, given S complement, which we just said was that the individual is using. Okay. Now, once I have it written out in the context of my example, it's just a matter of going up here and grabbing these probabilities I was given and plugging them in. Okay. So what's the probability that someone was not using? Right. Go up here. Probably that somebody was not using. Oh yeah, that's when we were kind of indirectly given, right? So that was 0.85. Okay. So come down here, the very first one, right? 0.85. The probability that the test comes back positive given the person's not using. So given that someone's not using, the probability the test comes back positive was 0.01. Right? So 0.01 there. And then we can kind of turn this into a fraction here to make our life a little bit easier to see all this at one time. Well, remember, the first part of the denominator was the exact same thing as the numerator. So we can just, even if we went through the process, we'd be finding those same values. The probability someone is using was 0.8. Wait, did I mix? Oh, 0.15. So 0.15 times, given that they're using, the probability the test comes back positive. So given that they're using, the probability the test comes back positive was 0.95. Now it's just a matter of getting that entered into our calculator. Okay. Any questions over any steps in that process? Okay. All right. I think I can do this real quick to double check, even though we have the answer key pulled up here. So we got what? 0.85 times 0.01. 0.15 times 0.95. Oh. 0.85 times 0.15 divided by. Hold on, I'm struggling over here. 0.85 plus 0.15. Given that they're not using, so we have 0.01, 0.85, 0.5, 0.01. Because I'm looking at the wrong problem. I was going to say, I'm not saying 0.056 is the answer. It's down here. All right. So if you end up doing that, you get that 0.056. Right? So I was looking at these. I'm like, I'm not seeing the answer I'm coming up with. Okay. So if you do that, get this entered into your calculator, you should end up getting about 0.056. Okay. So Bayes' theorem, like I said, if you go to use that general, like the easier kind of formula to find a conditional probability, and you're like, I don't have this denominator, that's a good indicator you need to use Bayes' theorem equation. Like I also said, the exams have a pretty similar order or the exam will have a pretty similar order as the practice exam. So when you're getting around these questions, you'll probably, if you're looking for conditional probability, probably start to think, I probably have to use that Bayes' theorem here at this point. Okay. Any other questions on this one before we keep moving here? All right, so the other ones I want to work through is kind of go through these contingency table problems. Okay. So here I have an example, right, where I've got my event A is, does someone want marijuana legalized? Yes. A complement then would be that they don't want it legalized. B, my event B would be that they're Republican or they're not. Okay, so I've got B and B complement. So these are my two events. I'm going to, kind of shorthand them, use R and LM. Okay. So first, I want to find this missing value for X. All right. So if I left out this cell here, how could I maybe find this missing value for X? Yeah. Yeah, so we know that if I left off the total columns, the way that we should do this is basically add across the rows or down the columns to produce those totals. So notice 0.15 plus 0.35 is equal to 0.5, 0.35 plus 0.1 is equal to that 0.45. Okay. So I can find X two ways, right? 0.15 plus X has to be equal to 0.55. That was adding across the rows. Or I could add down the columns so that X plus 0.1 is equal to 0.5. Right? And from there, in either one, it's just a little bit of algebra. So if I do this one right, subtract 0.1 from both sides, I end up with X is equal to 0.4. Okay? So this, hopefully, we can remember the way that contingency tables work. Should be some really easy points in the exam. If I left something like this off the table, you should be able to reproduce this fairly easily. Okay? Next question, right, is what's the probability that an individual wants marijuana legalized, given that the individual is a Republican, right? So we see this word given, right? So we should be thinking automatically, we're looking for a conditional probability. Okay? So I'm going to write this out first. So we want the probability, what are we given? That the individual is a Republican. So that my shorthand for that was R. If you wanted to on the exam, you could just write the word out, yes, Republican, or they are Republican. So given that information, what's the probability that they want marijuana legalized? LM, or that, kind of that table that marijuana legalization is equal to yes, or however you want to write this out. So I've got this conditional probability, kind of like the earlier one. I showed you where we couldn't use that equation, kind of easier one. Well, now I'm going to try to use it again, and I'll actually see, in this example, I've given enough information that I can use this simplified version, right? So this is like my A and my B. Right? So this conditional probability is just the intersection of these two events divided by what I'm conditioning on, which is that they're Republican. So now that I have this written out, those are two things that I have up here in my contingency table, right? So what's the probability that somebody wants marijuana legalized and they're Republican? Yeah, so they want marijuana legalized and they're Republican. That probability, the intersection of those two events, is 0.15. Remember, we said those top four left cells all represent intersections of whatever that row and column heading are. We then divide that by what we've conditioned on, which is the probability that someone is Republican, right? So that would just be 0.5. So we divide by 0.5, which gives us the answer 0.15 over 0.5 is 0.3. So we can, use these tables to find conditional probabilities. We can also use it to find simply the intersection of two events. So here, what's the probability the individual is not a Republican and does not want marijuana legalized? Okay. So what's the probability? And here, I'll kind of show you how I would write this formally. But if you wanted to, you could have just written in, the probability that marijuana legalization equals no, and the probability that Republicans equals no. If that shorthand's easier for you. The way we would really write it notationally is, what's the probability that someone doesn't want marijuana legalized? So I'm just going to call that LM complement, right? So they don't want marijuana legalized, so LM complement. And, right, the intersection, that term and means the intersection with not being a Republican. Well, if R is being a Republican, our complement would be not being a Republican. So what work do I have to do here?
Is it just adding the two nodes together?
So if I want an intersection, and I look at those top four left cells, they all represent intersections. I actually don't have any work to do here. It's kind of a trick question. Right? So I don't want marijuana legalized, and they're not a Republican. That probability is simply 0.1. So that's all I have to do if I'm looking for an intersection. It's going to be just one of the values in those top four left cells. Can't remember if I have what the next question is. Let me refresh my memory. Yeah, so I left one out of here, which is, I think, what you were thinking of. And I was going to go through an example. Also, this marker's dying on me, so let's try to do a different color over here. It's kind of faint. So what if I wanted the probability that somebody wants marijuana legalized, or they're a Republican? So now I want the union of two events. So I'll show you in a second. When I go back over, this is why I was thinking I could just sit at the table, but then I realized typing it out is somewhat boring. So I want the union of two events. That's going to be adding up the probability of each event, but then we have to subtract out what we double counted, which was the intersection. So I'll show you where that formula is at in the formula sheet in a second. But all we're going to do to find the union is add the probability of each event together, and then subtract out the intersection, right? So LM and R. Okay. What's the probability somebody wants marijuana legalized? 0.55. What's the probability somebody is a Republican here? What's the probability that they're both of those things? So yes, they want it legalized. Yes, they're a Republican. The intersection of those two is just 0.15. So put this into a calculator. Okay. Okay with that? So where I got that equation, I was doing it from memory, but you don't have to. Right? The union of two events, right, is just add up the probability of each event and subtract out that intersection. Right? So even though that's not a question on this practice exam, wink, wink, I would know how to find the union of two events using a contingency table. Like I said, I have the exams printed out, so I'm not just wasting air here. Yeah.
So what would be like a keyword to use union with in a question?
So if we're looking at these questions, give you a little summary here. It's a good question. Now I'll move out of the way in a second. All right, so anytime we see the word or this set symbol that looks like a U, we're looking at the union of two things. Anytime I see this word and, or I see kind of that upside down set symbol, I'm looking at the intersection of two things. Anytime I see this word given, I know that I'm looking at a conditional probability. So if I'm writing out that probability, I should have kind of this conditional line in the middle. Okay. Yeah.
And the word that would go after given would
Yeah.
be on the right side.
Yep. So whatever you're given goes on that right-hand side, which we'll make a point about this. We'll kind of, or I'll dive a little bit deeper into this in the next couple of questions, but yeah. Any other questions with that? That's a good question. This would be something good to have, like, so yeah, to kind of have in your mind. So the next two questions on this exam, practice exam, are, we'll kind of skip 8 for a second because 9's a lot easier, and then we'll come back to 8. So are wanting marijuana legalized and being a Republican mutually exclusive events? So first of all, is everyone okay if I erase this? Okay. So anytime we're looking for the whether or not events are mutually exclusive, the definition we had was that if they're mutually exclusive, they can't happen at the same time. So if they can't happen at the same time, what I'm thinking about is that these two events, they can't happen at the same time. What would the probability of their intersection be? 0. Yeah, if something can't happen, the probability is 0. They can't happen at the same time, there's no overlap. Right? So the only way that two events will be mutually exclusive is if we see a 0 up there in the contingency table. I can scroll up, but if you remember, I don't have any zeros here. Even when I solve for X, I don't have any zeros. Now, specifically, what I'd want to know is the probability they want marijuana legalized and being a Republican 0, right? But I don't have any zeros here. Okay, that intersection is not 0. So I would say that no, they're not mutually exclusive. The only way they're mutually exclusive, right, is if that intersection is equal to 0. So if they are not, that intersection is not equal to 0, we would say that it's not mutually exclusive. So we're looking here, we didn't see a 0, so automatically we should know, no, they're not mutually exclusive. But the reason why we knew that is because the intersection, it doesn't matter what order we write it in, right? That was one of the other rules we said, like it doesn't matter if I sell LM and R, R and LM. We know that they're not mutually exclusive because that intersection was not equal to 0. Okay? The union being not equal to 0 doesn't tell us anything. Right? It doesn't necessarily mean they're mutually exclusive. And even if we look down here, yes, well, this one doesn't even make sense because if the union is equal to 0, that still doesn't tell us anything about the mutually exclusive events. In fact, this is kind of a weird one, but the union of two things is equal to 0. What would that mean? Actually, it would mean that neither of those two things can happen. So I mean, that one doesn't even really make sense to us, right? The union of two, is it this or this? Well, probably 0. That means I could never see either one of those events. So that the answer doesn't even make sense for anything. Now C makes a little bit of sense. Yes, and we're looking at the intersection. But if in fact they were mutually exclusive, what would the intersection have to be equal to? So this answer actually doesn't make sense. So we could rule out C and D right away. In fact, we could rule B out too. None of the other three make sense for the definition of what mutually exclusive is. Yeah. Any questions on that before we keep? So the key there is for mutually exclusive, they are only mutually exclusive if that intersection is 0. If it's not equal to 0, then no, they aren't mutually exclusive. So number 8, which is a little bit tougher, mutually exclusive. Mutually exclusive is kind of easy to check. Can I get rid of
quick question?
Yeah.
So say if it said R1ing, I don't know if that will make sense, but R1ing marijuana legalized or being a Republican, would the answer be
So
B?
So this is a little bit weird, right? So I understand your confusion. So what might be a better way? So this word "and" isn't referring to an intersection, right?
Okay.
It's just like the way we're using it in English. So you might, maybe an easy way to think about this is, hold on. Are the events of wanting marijuana legalized? I can't even say that without saying the word "and." Do you understand what I'm saying though? Like it's just referencing these two events. So just the way we speak in English, I can't reference, but I would almost have to say, like, is the event of wanting marijuana legalized and the event of being a Republican independent events. I'd almost have to like use something like that.
Yeah, I get it.
Okay. Yeah, when we're referring to mutually exclusive, like the definition, then that this "and" isn't like implying like what's the probability of this and this, right? We're just saying these are the two events. Are they mutually exclusive? Yeah. It's a good question. I've never had anybody ask that, but that's an English, the way that we speak, that does kind of cause a little confusion. Any other questions on that one from people? Okay, so let's think about independence. So that was the another definition we had that we might want to come up with. So can I tell from the contingency table if two events are independent? So if we go back, the definition of events being independent is if having information about one event doesn't change the probability of the other event occurring. So this was the idea, and I'll kind of write it out not in the context of this example first, and then we'll kind of transition to thinking about this specific example. All right, so we said here we had the unconditional probability of A, and here we had the conditional probability still of A. Right? So we're conditioning on that B has occurred, but we're still thinking about the probability of A. So whatever's on the right-hand side, that's what we've conditioned on. Whatever's on the left-hand side, that's still what you're looking for the probability of. Right? It's just now, instead of being an unconditional probability, it's conditioned on whatever's on the right-hand side there having occurred. Okay? So if these two things are equal, we would say that they're independent, right? Having information about B, because these two things move independently, doesn't alter my probability of A at all. If they're not equal to each other, what that's saying is if you give me information about that B has occurred, well, that fundamentally changes the probability that I now see A, right? And this is honestly, so this would be like they're dependent or they're not independent. And this is probably most situations that we deal with in real life, that two things are probably not going to be independent. But you never know. And since I'm choosing these numbers, it's a little bit easier for me to make things independent than in the real world. So we want to check to see if things are independent. Here, what we're thinking about is, and I'll show you something that can kind of be confusing about trying to determine this. Not B, our event was R. Right? So we're going to check to see if the unconditional probability of wanting marijuana legalized is the same as the conditional probability of wanting marijuana legalized, right? We'll condition on whether or not they're Republican. So how can we check this? Well, if we go up here, what's the probability that somebody wants marijuana legalized? Unconditional probability. We just go over that total column, right? So the probability they don't want marijuana legalized, 0.55. Now we can't directly get this probability from the table, but actually, we can solve this using components in the table, because we said earlier that if I want a conditional probability, that's the same thing as the intersection of those two events divided by what we conditioned on. I think we might have found this earlier, because the intersection of these two events is what? 0.15. The probability of being Republican, not 0.3. What is that? That's 0.5. And that's where we found in that earlier problem that ended up being that conditional probability was 0.3.
are independent, does that mean they're going to be mutually exclusive or not?
Come back to that in a second. It's a good question. We'll finish this thought, but that is good. So this, we found this conditional probability is 0.3. So is the unconditional probability the same as the conditional probability? No. So we would say that they are, right, not independent, because the only way they're independent is if those two probabilities were the same. Okay. So we're looking down here at the answers, right? Are they independent events? Well, we just found no, they're not, right? And now we just have to choose the correct justification as to why. Now, I solve for a little bit different than the answers are displayed. But if I find that the unconditional and the conditional probability of LM, if that's not equal, those two events aren't independent that way. If I checked it the other way, I could have also checked to see, right, is LM independent from R, or I could have checked to see is R independent from LM, right? Either way tells me that these events are independent. It's just a different way of checking, right? So the way that the answers are displayed here, we actually would have to use the justification that the unconditional and conditional probability of R aren't the same. Right? So we found the answer of no, but we didn't check it the way that the answers kind of had it, at least in the order in which they had it. But that doesn't matter. As long as we check it one way, we know whether or not they're independent or they're not independent. So we found that they're not independent. And if we think about this first justification, one thing we have to make sure is we're comparing the conditional and unconditional probability of the same event. Here, this answer is comparing the conditional probability of R to the unconditional probability of LM. That doesn't tell us anything. Probably tells us something. We want to dive deeper into this, but in terms of the definitions we have, that doesn't tell us anything, right? So we have to make sure that we're comparing the conditional probability of something to the unconditional probability of that same event, right? So here, these two kind of make sense because at least they're comparing the same, event, the conditional, unconditional probability of the same event. The reason though we know these aren't true is because we already checked to see if they're independent, and we found they weren't, right? So we know they weren't independent, and then from there, A doesn't even make sense because it's not even comparing the unconditional and the conditional probability of the same event. Right? But technically here, right, this could have been a correct answer, or this could have been a correct answer, right? Because all that's saying is that R is independent from LM, which would also mean that LM is independent from R. Okay. Lost my cap. Any questions on that before I kind of move on to that question? All right, so it's a good question about if events are mutually exclusive, can they be independent or vice versa? So let's think about that. So we've got our definition over here. And I'm going to write that out. So probability of LM. Instead of writing it the conditional, I'm just going to plug in that equation there. So I said the conditional probability of LM given R was the intersection of those two events divided by the probability of what I'm conditioning. So all I did there was this is kind of my law of independence. But for that conditional probability, I just plugged in that equation I know will give me the conditional probability. So if I had mutually exclusive events here, what's going to be true, remembering that this represents my conditional probability. If I have mutually exclusive events, can I have independent events? No, right? Well, theoretically I can, but for the most part, no, I'll tell you why. So if they're mutually exclusive, what has to be true about this numerator? It's 0. Is 0 going to be equal to the probability of an event occurring? Not unless the probability of that event occurring is 0, which is Why are we, we're not interested in events that have no likelihood of occurring, right? So if they're mutually exclusive, almost automatically, right, we're not going to have independent events, right? Unless the event probability itself is 0, which just is very rare, right? Now they could be independent, right? These two things could be equal, right? And they would not be mutually exclusive, but we could never see that we have independent events, but they're also mutually exclusive. We would never, unless we had this really weird scenario where the probability of the event we're interested in is 0 itself, which just doesn't happen in practice. So yeah, just because they're independent doesn't necessarily make them mutually exclusive. In fact, they are independent, means that it can't be mutually exclusive. Other questions kind of related to either of these definitions? So we got a lot of probability stuff. 25 minutes. I'm gonna decide. I think I'm gonna switch practice exams here. Potentially. Oh no, I was looking at B already, wasn't I? Let's look at A for a second, because I think there's a specific problem I'd like to go over. Okay, yeah. Let's deal with a discrete random variable. So the other one is like literally almost the exact same example we went through in class. So I just want to give us a slightly different example to think about these discrete random variables. So here I've got a discrete random variable, which is the number of weeks someone gets sick in February. So it's February because it's nice because we got 4 months, 4 weeks, right? So you can either be sick 0 of the 4 weeks, 1 of the 4 weeks, 2, 3, or 4, right? And I think about it, even if I'm sick 1 day a week, I was sick that week, right? So the probability that those things occur are kind of given to us right here. And then we're asked, what's the expected number of weeks an individual is going to get sick in February? Kind of that expected value is the mean of that discrete random variable. Okay. So if we want the expected value, we go to our formula sheet. We've got our discrete random variable equations here. This one is for the mean. This one is for the variance. So to get that mean, or that expected value, all we're going to do is go through every outcome, multiply it by the probability we see that outcome occur, and then add them all up. Okay? So for this one here, all that's going to mean, going through, take that first outcome of 0, multiply it by the probability it occurs of 0.45, add to that the next outcome of 1, multiply it by the probability it occurs, which is 0.25, then just kind of continue this process until we run through every single possible outcome. Right? And it's as simple as that. We don't have a denominator because it's kind of like a weighted mean, right? We're using these probabilities as our weights, but the sum of our weights here, we add up the probability of every outcome, they should just add up to 1. Right? So we don't really have to worry about a denominator. Well, what is this going to be? 0.25 plus 0.3 plus 0.3. So what? 0.85 plus 0.2. So 1.05, if I'm doing this math in my head correctly. Right? Now, what you don't want to do is simply add these values up and divide by 5. That's kind of how we would treat a typical mean calculation. But that's only if every outcome would have been equally as likely. Here, they have varying degrees of probability of occurring. So if we find add them up and divide by 5 with the normal mean, I believe I'll get 2 there. But that doesn't factor in that some of these outcomes are more likely to occur than others. Okay? Now, I could probably rule A out. I mean, depends on how well I can think about math. But in order for A to be the correct answer, what would have to be true about the probabilities I have here? Yeah, 0 would have, it is the most, but it have to be really, really likely, right? Yeah. It'd have to really have a high probability. Probably something like 0.8 or 0.7, I would guess, somewhere in that range would probably be high enough to get us there. But, we're looking for that middle value. But the values that have higher probabilities of occurring are going to influence that mean a lot more. Okay. Any other questions on that one? Yeah.
How would you go about finding the variance for this one?
Yeah, so I'm sure that's probably the next question. I don't know, but if it's not, it's definitely a question I could ask. Yes, so standard deviation, but same idea. So usually this is what I'll do. And if you look at the first couple problems of the exam, we're not going to go through them today, I would imagine. But I also don't want to waste time because hopefully finding like the mean, the median, and going back and just doing the variance, those are a little bit easier. Okay? So anytime I ask you to find a mean, and then I also ask you for that same data set to find a standard deviation or variance, if you got the mean wrong, you're going to have cascading errors because you need the mean to find the variance of the standard deviation. So what I do, right, is I give you an assumed true mean, right? So don't read into these assumed true values at all. Notice I told you to assume the average or the mean you found before was 2. It wasn't 2. In fact, 2 would have been the wrong answer if you went and answered it, right? So I'm choosing these values completely independently of what the correct answer is. In fact, sometimes I choose them to be like very unlike what the correct answer actually is. Okay? So I've got this, assume the average of 2. So we're all starting off on the same place, regardless of what answers we got for 14. So the way that I'll find this variance is I'm going to go through each possible outcome. I'm going to subtract that mean, which I've been told is 2, square that deviation, and then multiply that by the probability I saw that outcome occur. So I think we've got the probabilities over there. So I'll scroll up in a second here, but we'll go to that first outcome, which was 0. I'll subtract the mean and square. Unlike a regular variance though, I then need to multiply by the probability I saw that outcome of 0 occur, which if I remember correctly is 0.45. Now, one good practice doing this, if I go back up to that table, I could do this for every single observation, like, and write another column in where I'm kind of doing the intermediate calculation. So 0 minus 2 squared times 0.45, and then write that number down. 1 minus that mean of 2 squared times 0.25, write that number down, right? And kind of continue to do that, whoops, all the way down. So the next outcome we could have seen was 1, subtract that mean, square it, multiply it by the probability we saw 1. I remember over there is 0.25. 2 minus 2 squared times the probability it occurs. I think that was 0.15. Next outcome was 3, subtract the mean, square it. Probably we saw 3 was 0.1 over there. And then finally, 4 minus the mean of 2 squared, multiply that by the probability we saw 4. I would then add all those values up, and that would give me my variance. I don't know what it is off the top of my head. I think figure this out. I'll do it with my calculator in a second, because I want to make a couple of points before I go back up. Which of these answers can I rule out right away?
Negative.
Yeah, right. If I'm looking for a variance or a standard deviation, the lowest they could ever be is 0. 0 variation, right? Just like the lowest the probability can ever be is 0. So we know it has to be a positive value. From there, it's a matter of doing this calculation. So we have what? 4 times 0.45, or sorry, 2 squared times 0.45. Line all these up. If anybody gets it done before me, let me know. So we've got what? 4 times 0.45, 0.25. I think it's 2.35. If anybody wants to check me, if I did that math incorrect, let me know. I think that's the variance. It kind of makes sense with the answer up there. But is that my answer? No. I read these carefully. I wanted the standard deviation. So what's the only other thing I have to do? Take the square root, right? So if we're doing a typical variance, we divide by the total number of observations, or divide by, if it's a sample, divide by the total number of observations minus 1. But the key difference here is going from the variance to the standard deviation. No matter what type of example we're looking at, we take the square root of the variance. So here, that standard deviation would be the square root of 2.35, which I'm guessing is 1.53. Okay. Any questions on that?
So the square root is what gets you from the variance to standard deviation.
Yeah, so you should like tattoo this on the thought, right? To get the standard deviation from the variance, all we do is take the square root of that variance, right? And then, you know, we never, for this first exam, we're never really working backwards. We're never like trying to get the variance from the standard deviation, because to calculate the standard deviation, we have to go through the process of calculating the variance, right? And in that final step, it's almost like, okay, we've got the variance, we just want to scale it down, so we'll take the square root and that'll give us a standard deviation. You know, up to this point, we're never like given the standard deviation and have to go backwards to find the variance. So we have to worry about that for now. For the next exam, we'll start to sometimes work backwards, but for now, we're always going to have to calculate the variance and then take the square root of the standard deviation. Any other questions on that? You know, so the only difference between this, like in the regular variance, is we don't have to worry about all these probabilities. And then, like you said, we would be dividing by total number of observations if it's a population, total number of observations minus 1 if it's a sample, right? Which you'll see in the first 3 problems on this exam. Here I ask you for a sample standard deviation, right? So that would be, you know, I'm always going to like, often if it's the difference between population and sample, I'll bold or underline or make sure you can see this is a sample standard deviation or this is a population standard deviation. But when it comes to a discrete random variable, we don't have to worry about that denominator, because it's essentially, so we've got our, here's that the equation that we really were following, but this is essentially a weighted variance, which we have over here, but our weights are probabilities. So the sum of our weights, or the sum of the probabilities across every possible outcome, should always be 1. So we essentially can ignore that denominator. We've got a discrete random variable. And the way we identify that we have like a random variable is the different X outcomes have different probabilities of occurring. And whenever we see probabilities, we should be thinking this is a random variable. Sorry, probabilities associated with different values for X. I should say that, because we have probabilities with contingency tables and those aren't random variables. So that was, I was working off of practice exam A. Oh, I went too far. Where am I at? Yeah, there we go. Now this will hopefully be an easy points on the exam, right? But if I had something like this and I asked you, what's the probability someone is sick for less than 2 weeks? So what's the probability X is less than 2? So for this example, what are the only outcomes that fit this criteria? Yeah, if I want the probability that X is less than 2, this is a discrete random variable, the very first outcome I can see that meets that criteria is that X is equal to 1. And then the lowest kind of outcome I had there was that X was equal to 0. So all I'm going to do is go up to the table, find the probability of those 2 events. All right, so that's what, 0.7, if I add up 0.45 and 0.25. And I'm done. Okay. It's as simple as that. So when it comes to these like just general discrete random variables, these kind of problems should be pretty easy. Identify the values for X that fit that criteria and just add the probabilities up. Okay. There's no overlap because we either see someone be sick for exactly 1 week or exactly 2 weeks. Can't be sick for just 1 week and just 2 weeks. It doesn't work that way in the way in which we define this variable. All right. Any questions on this? I'm trying to think if there's anything else I want to say on this before we keep moving. All right. So that kind of is that batch of questions. Let's do these. We'll stay on practice exam A here. So let's say 64% of people have a visual impairment in the US. And we are looking for out of 15, right? What's the expected number of people who have a visual impairment? Okay? So people either are visually impaired or they're not. we've got a capped number of people we could see here. The highest number of people with a visual impairment out of these 15 would be 15, right? We know that we're capped at that amount. And the underlying probability of success that someone has a visual impairment here is the same across individuals, right? So if I select one person at random, the probability that they have a visual impairment is 0.64. So we've got a really nice setup for a binomial distribution example. Okay? So the expected number or the mean, if we can't remember, well, if I had 100 people here, what would be the expected number of people that have a visual impairment? Yeah, 64. And the reason why is a little bit easier to think about really what we're doing in our head there to find that mean. And here's our equations for a binomial distribution example. We're really just taking the number of trials times the probability of success. So it's a little bit harder when I don't have like nice kind of n's that are 100 or 10, but really the equation is not that difficult. Right? So if I do this here, I think it's 8 point something. Probably if I look at the examples, so I know it's going to be 9.6. Right? And if we just think about what we're doing here, like we're looking for the expected number, the average number of people out of 15 who would have a visual impairment. So 15 here doesn't make a whole lot of sense unless the probability that someone has a visual impairment is what? 100%, right? So hopefully we can rule D out right away. Right? From there, it's a matter of can we get this underneath. Okay? Any questions on that one? That one should be no, this is another one that should be really easy points, especially since to win over it relatively near to the exam. So let's think about what we're doing here for a second. What we really just said is, okay, we've got the mean is 9.6. So if I think about the values of 9 and 10, those will be the most likely outcomes, right? And then as we move to number of outcomes that are, or number of successes that are further from that mean, right, of 9.6, those probabilities will be declining, okay? So if I want the probability that exactly 10 people have a visual impairment, right? Well, it seems like, that should be relatively high. It's one of the most likely outcomes. Both 9 and 10 are kind of our most likely outcomes. So if I'm looking at these probabilities, it doesn't seem like it really should be as low as 0.1. But if I think about a probability of like 0.89, well, if these two are the most likely outcomes, even if they exactly split all of the possible like probability area, they would both be 0.5, right? So the probability of seeing exactly 10, 0.8 seems like way too high. Right? I mean, with a mean of 9.6, these are the two most likely outcomes, right? But I doubt that they're like that mismatched where one of them's like 0.89, the other one's 0.1, and the rest of the outcomes are like 0.0001. Right? That doesn't make sense for the example we looked at. So I probably would rule out D, and C seems unlikely, right? But from there, it's really just a matter of using that binomial distribution equation, right? So our X here, we're looking for the probability that we see exactly 10 people have a visual impairment. Right? So from here, I mean, this might just be a little bit of kind of practice on our own. I mean, I can write this out for you, but right, you're just plugging in 15 for N, 10 for X, and that probability of success of 0.64. Okay? So, I was kind of, as we were working through these examples, I suggested maybe breaking this down into parts and kind of like finding this is equal to, this is equal to, and then multiplying them by each other, like doing this kind of in steps, might be one way to kind of avoid making too many mistakes. Enter this all in your calculator in one line. Doing the easy math first, like N minus X here, 15 minus 10, hopefully we know that that's just 5, right? We can just write that in instead of dealing with parentheses. The factorial, right? Hopefully by now you've kind of identified where that button's at in your calculator. If not, when we write this out, a lot of things will cancel, right? We can write out what those factorials are. And with numbers that are kind of as low as 15 or 10, that's not too terribly cumbersome. But, it would help if we kind of were able to use that button on our calculator. So if you're having trouble finding that, feel free to reach out to me over the next 48 hours, preferably not, right before Wednesday's class. but that would make it a little bit easier. From there, it's really just being comfortable plugging those values in that formula and entering that into our calculator. Okay. Now, one thing I might do that helps you kind of eliminate some answers here is, let's say instead of 10, I asked you for like, what's the probability that I see 5? So right away, what answers could you rule out if I asked you for the probability that 5 of these 15 people had a visual impairment? Kind of already alluded to it, but right, A and D. So why? If the probability of seeing 5 was in fact as high as 0.6 or 0.8, that means that 9 and 10 couldn't be the most likely outcomes, right? There's only like 0.4 remaining. And if it gets split up between these two most likely outcomes, well, they're no longer the most likely outcomes, right? That would make 5 the most likely outcome. And we know based off of the, where is it? The mean, if the mean, is 10, right? Then that expected number of successes, 10 would be the most likely outcome. But if it's in between two, we know that those two values, 9 and 10, have to be the most likely outcomes or have the highest probability of occurring. So if something other than those values had a probability over 0.5, that's impossible. Those could no longer be the most likely outcomes, right? So sometimes doing something like that would kind of help you identify like, yeah, A and D don't make any sense. In fact, 5 is so far away from that expected value, I would probably choose the lowest probability that I could find up there. I don't know what it is, without doing the computation. But my guess is if you find the probability X is equal to 5, it's probably much, much lower than 0.1. Right? It's probably pretty close to 0. Okay. And if I ever give you an example where you do have a probability that is really, really small, instead of writing like 0.0001, I'll probably write approximately 0. Anything that would go out past 4 decimal points, where you would just see zeros for the first 4 decimal points, I'll write in treat that as though it's approximately 0. Okay. Any questions on that? I'll try to do this one more before we finish here. Yeah.
Can you explain why you cancel out A as an answer again? Why you say?
Yeah. So I only would cancel it out if I was looking for the probability X is equal to 5. So think about it this way. I know these are the two most likely outcomes because the mean is 9.6. If the probability of seeing 5 was 0.6, how much is remaining? 0.4. Even in a world where, let's just say that the average was 10 and that I knew 10 was the most likely outcome. Well, if the probability of seeing 5 was 0.6, I mean, even if all the remaining probability went to 10 and the probability of 10 was 0.4, it would no longer be the most likely outcome, but I know it has to be the most likely outcome. So I'm like kind of doing this like, assuming this was the right answer, could this still be true? And it can. If it's anything over 0.5, there's no way that could, that 10 could still be the most likely outcome. Yeah. Any other questions on that one? So I'll briefly mention here real quick. I won't work through the entire thing, but I do want to make you aware. If I'm looking for something like 19, where the probability that X is less than 14, thinking about this as event A, well, that would be the probability X is equal to 13 plus the probability X is equal to 12 plus 11. Every time I want to find a probability of a certain number of successes, I have to use that binomial equation. I doubt I'm going to expect you to use that equation 14 times, right, on these. It just takes too much time. But what could you also do here? The probability of any event is 1 minus its complement, which the complement here would be X is greater than or equal to 14. The only two outcomes that fit this criteria, X is equal to 14 and X is equal to 15. So you could use that equation twice, find the probability X is equal to 14, find the probability X is equal to 15, add them up and subtract from 1, right? So, you want to save yourself a lot of time in the exam, using that complement rule can do that. Okay, so that does it for us. We'll meet here in class on Wednesday. I'll hand out the exams, hand out the formula sheet, blank pieces of paper if anybody wants some, and the Scantrons, and we'll go from there. Okay. you have any other questions, tomorrow, or you want to meet up, feel free to send me an email. We can try to find a time tomorrow that works. Only time I'm busy tomorrow is from like 1 to 1:45. So feel free to kind of reach out. Okay. Good luck with studying, and I will see you guys on Wednesday.